Based on the requests made by most of you that you people want me to make a video of the MOS capacitor, so here is it. So basically, what is a MOS capacitor? MOS capacitor, if we decipher the words, it is metal oxide semiconductor capacitor. For most of us, this term appears to be heard for the first time, but if I tell you that you people have already studied most of the physics of the metal oxide capacitor, because this metal oxide capacitor is simply a MOSFET, which is the metal oxide semiconductor field effect transistor, and which we draw like a device having a semiconducting substrate, whether it is N-type or whether it is P-type, and it has two heavily doped source and drain regions. In between the source and the drain, on top of it, we have the gate oxide, and on above the gate oxide, we have the metal gate. So like this. So let's take, so this becomes the gate terminal. This is our source terminal and this is the drain terminal. Now depending upon whether the MOSFET is N-type or whether it is P-type, we can have source and drain dopings as N plus or P plus respectively. So that means if we are designing an N-type MOSFET, if we are designing an N-type MOSFET, then the source and drain regions are both N plus, and the substrate is only P-type. Substrate is only P-type. Whereas in case of the P-type MOSFET, we have the reverse. That is, if it is P-type, if the MOSFET is P-type, we have source and drain as P plus, that is heavily doped P regions, and the substrate as N. The substrate is N. Now, in between the this semiconducting material, whether it is N or whether it is P, and similarly source or drain can be okay, I should have written P plus, in accordance with whether the substrate is P plus or whether it is N plus. P plus or N plus, right? Yeah. So in between the semiconducting material and the gate terminal, we have an oxide layer which is an insulator. Particularly we are using silicon dioxide, but it can be any other high K gate dielectric material as well. So we have between the gate terminal and the semiconducting substrate, we have the gate oxide. So if we view this system in terms of the energy band diagram, we will see that if the source and drain regions are chosen to be P plus and the substrate is then N, then obviously the position of Fermi level in the P plus source and drain will be different from that of the substrate. But when these all are combined together, that means when the three different materials are put together, the Fermi level is just a single line in any system, because three different materials combined together becomes a system. And when the Fermi level is a single line in this system, the bands have to adjust accordingly. Like in the case, if we take a closer picture at this structure of the MOSFET, it is, let's suppose we take it for an N-type MOSFET. So for an N-type MOSFET, we have N plus source, an N plus drain, and a P-type substrate. Now in an N plus source and a drain, if I draw the energy band diagram separately, it will be something like this, where this is the top of the valence band, this is the bottom of the conduction band, and let this be an intrinsic Fermi level, EFI, in intrinsic Fermi level, but the position of the Fermi level in case of an N plus semiconductor will be closer to the conduction band. So it will be like here, maybe. It is EFN. Alright, and for a P-type material, I draw again the energy band diagram, the same. Here EFI is only taken as a reference position in order to see whether the Fermi level lies above or below or closer to the valence band or the conduction band. If you people are comfortable with this, we can even do away with the intrinsic Fermi level. So for a P-type, obviously the Fermi level will be much closer to the valence band. So this is EFP. And again for an N plus material, it will be, this is EC, this is EV, and again the Fermi level will be somewhere closer to the valence band, which is EFN. Now we're saying that when three different materials or two different materials are combined together, but here we have three materials being combined together, because in between the two materials of the same type we have two Fermi levels, three Fermi levels rather, that is for N plus source and drain regions, and for the P-type substrate which is there. Now the question is that how these Fermi levels which are at different positions will align, and how will the bands change. See, okay, now this is the system. Now here I will be drawing a single Fermi level, which I'll call as E. Okay, let me use another color. EF. Now it's not EFN or it's not just EFP, it's simply EF. Alright, and let me take the N side. The Fermi level along the N side is closer to the it's closer to the conduction band. Okay, along this side it's again closer to the conduction band. It's just a freehand straight line. We can draw it precisely like this. Yeah, okay, let me draw it again. Okay, alright, and extend it to here. So this is the conduction band EC along this side, and this is the conduction band EC along this side. Which side? That is the EC. Okay. And now what do we have is that now the Fermi level which is here for the P portion is here, but in the P side the Fermi level is very close to the valence band. So we are going to draw the valence band here like this, because the position of the Fermi level will not change. Okay, and it is here, and then accordingly our conduction band for the P portion is here, and along the N plus source and drain what we are left with drawing is this EV, that is this EV. Okay, now what we are going to do is we are going to draw this EV here, this EV here. So this is our EV. Now when it forms a system, we have a single Fermi level. Next, what do we need to do is we need to simply join the conduction bands of P and N, the valence bands of P and N. So how do we join? This is the conduction band. I'll remove a certain portion so that I can make a smooth transition, which is like this, and then again a transition which is like this. So along this side I draw a smooth curve. Okay, let me draw it smoother. I draw a smooth curve which is like this, and then again I draw it like this. So this becomes the energy band diagram of a complete system. Now let's see. The intrinsic Fermi level for the N plus side will be along, let me draw the intrinsic Fermi level with the blue color. So this is our intrinsic Fermi level. Okay, along this side, and this is our intrinsic Fermi level along this side, and here we have the intrinsic Fermi level which is along this side. So if we join these intrinsic Fermi levels like this, the difference in the position of these intrinsic Fermi levels in N and P, let us say it is Q phi, denoted by Q phi. So this Q phi is actually our built-in potential barrier. That means the electrons which are present in the conduction band of the N plus will see this much, that is the height of this slope, that is this will act as a barrier to the electrons. So this much of the voltage, or you can say this much of the energy difference, is to be applied so that the electrons can move from this N plus side into the P side, and similarly like this. So if this is source, this is drain, and this thing is our substrate. So this becomes the potential barrier height. You can see the difference of the value of the slope, or the difference of the energy levels like this. And similarly also there you have we can have the holes in the valence band, or we can have even the electrons in the valence band. These electrons can move to the valence band of the another substrate and so on. But moreover, we are interested in the movement of the electrons because this is an enhancement mode MOSFET. Obviously the electrons will be in majority and holes will become the minority carriers. Right, so this is actually the formation of the energy band diagram when three different materials are combined together. This happens in a MOS capacitor. So this thing, like where we are joining the conduction band edges of two different materials, or the valence band edges of two different materials, or even we are, like kind of analyzing the difference in the intrinsic Fermi levels of two different materials, is actually known as the band bending. So this is band bending. Actually, the bands are bent. You can see the picture was like this. We had straight bands, and then when we combine them, it forms a system. When a system is formed, the bands are bent. With this, we'll proceed next to the ideal MOS capacitor energy band diagrams. Now, what a MOS capacitor is, I told you that it is a MOSFET, but it's a vertical MOSFET. That is, we rotate the MOSFET by 180 degrees like this. So if we rotate it in this direction, what will happen is we will have gate on one side, then oxide, and then this substrate, whether it is P or whether it is N. So the resultant diagram will be somewhat like this. This is our gate, then oxide, this one, this forms the gate, metal gate, this forms the oxide, and along this portion it is the semiconductor. So if we have an N-type, for an N-type MOS, we'll have a P-type substrate. So for an N-type MOS, we have a P-type substrate. So this is our metal gate. So it is I'll just add metal gate. Okay. So this metal gate forms the one plate of a capacitor, and the semiconductor forms the other plate. So the equivalent is like this. It's a parallel plate capacitor. Okay. Very simple now. We need to analyze now the energy band diagrams of the MOS capacitor. We all know how the MOSFET operates. That is the MOSFET operation. You have studied it in the VLSI design, and you have studied it in basic electronics, you have studied it in solid state devices. So we all know MOSFET operation. MOSFET operation has three modes of operation we have. What is that? We have accumulation. Second mode of operation is depletion. And then we have inversion. And remember, here we are talking about the enhancement mode MOSFET. So we are talking about enhancement mode MOSFET. Now, what is accumulation? Accumulation is when the gate voltage is less than 0 volts for, again, an N-type MOSFET with a P-type channel. What is depletion? Depletion mode occurs when VGS is greater than 0 volts. Then inversion. Inversion is when VGS is much greater than 0 volts. Or we can put it like this, that VGS is greater than 0 but less than VTH. That is VTH greater than VGS greater than 0 volts. And here VGS greater than or equal to VTH. Now what is this VTH? VTH is a very important parameter in the MOSFETs, which is known as the threshold, It is known as the threshold voltage. So we'll be taking this accumulation, depletion and inversion one by one, but I'll be discussing only the energy band diagrams of these three modes, because the operation of MOSFET in these three modes I presume that you have already studied it in your VLSI design in your previous semester. So accumulation says that VGS is less than 0 volts. So what do? Is we again draw this diagram, that is we draw a metal plate here, oxide is in between, and along this side is our semiconductor. So this is a metal gate, this is our oxide, and this is our semiconductor. In this case the semiconductor is p-type. Alright, now for the metal we are going to denote Fermi level EFM. And since the substrate is p-type, therefore the Fermi level will be somewhere closer to the valence band. So it is like this, EFP. Now in the band diagrams we need to include some terms which are known as the work function. It's denoted by phi subscript m. So in terms of the charge, multiplied it by the value of charge, we can write it as Q phi m. And this work function is the energy required to move an electron from the Fermi level to the vacuum level. Okay, that's all written in your book. That's a solid state electronic devices by Donald A. Nieman. Sorry, by Benji Streetman. Solid state electronic devices by Benji Streetman. So, and since oxide has a very large band gap as compared to the metal or the substrate, so we show a discontinuity like a large value like this. That means it goes to the top end. We can denote this as the vacuum level, E vacuum, or we can just write it as E oxide. Now the work function of the metal will be measured from Q phi m, from the Fermi level to the vacuum level. Similarly, Q phi p, it will be measured from here to here. So if we look at the diagram, we can just see that Q phi p is greater than Q phi m. Okay, and for the reference purposes, if for the better understanding, we can also draw the intrinsic Fermi level, which in the case of a p-type will be somewhere here, EFI. Okay, and let's have another quantity, which is phi s, which is the surface potential. That is the amount of energy by which the bands have bent along the interface. See, this interface is very important. This is the interface. Interface is that portion where the two different materials are bound together, or where the binding of two different materials takes place. So because the effect of this voltage will be mostly on this area, not here, because it's the depth x. It's actually not x, it's actually y, because we have rotated the transistor by 180. We are measuring another quantity, that is Q phi f, which measures the energy difference between the Fermi level of the material and the intrinsic Fermi level, which is this difference, that is this. This becomes Q phi f. So all these quantities we'll be using in the band diagrams. Now what will happen in the accumulation mode? As we have discussed that VGS is less than 0 for which mode? Accumulation. Now how do we define this accumulation? Accumulation is defined when the carriers which are present in the semiconductor, that is the majority carriers which are present in the semiconductor, get accumulated near the surface. That is, their population increases near the surface. Now how will this happen in an N-type MOSFET? Is alongside the metal gate, the oxide. Okay, let us draw it like this. Okay, alongside this, so this one we'll draw first as the oxide. And it's EFM. And what do we have? We have, alongside this, we have EFP. And then Q phi m, that is a modified work function which is multiplied by Q. The Q phi m, then Q phi p. Okay, as you can see this whole thing from the diagram which is given in the book as well, which is this one, that is the two Fermi levels EFM and E of Fs are both aligned. They are aligned. That is what is here. And then below this we have EV, that is the conduction valence band, and we have somewhere EC, that is the conduction band, and in between EC and EV we'll have the midway. At the midway we'll have the intrinsic Fermi level EFI. So I reiterate that it's a reference energy level only. Okay, and then alongside the metal we just have the metal Fermi level. This position holds for the MOSFET when it's in the equilibrium. So this position holds when it is in equilibrium. Equilibrium means when no external electric fields are applied, that is when VGS is equivalent to 0 volts. Now we'll take the case when we are applying VGS less than 0. That means we are applying a negative potential on the metal side. Now since this is a parallel plate capacitor, if we are depositing negative charge on the metal plate, which is the gate, then an equivalent amount of the positive charge will be induced on the substrate, which is adjacent to the oxide. That is along this interface. An equivalent amount of positive charge will be generated. I'll rub it here. So what will happen when we'll apply this negative potential on the metal gate? When negative potential is applied, it raises negative potential, raises the electron energy, and it depresses the electrostatic potential that is related to the holes. It reduces the energy of the holes because we are applying negative potential. So what will happen eventually is that the Fermi level will move, or it will shift from this equilibrium position to some other level depending upon the applied voltage. If the applied voltage is V, then obviously it will shift by an amount of QV and it will reach somewhere here. And similarly, on this side, when we have the positive charges which are induced into the semiconductor, which is obviously a p-type semiconductor. Positive charge means, p-type means we have holes as the majority carriers, and positive charge in itself means again the holes. So obviously that is why it is said that charge carriers get accumulated. That means the population is increasing and they are accumulating near the surface. So how will the band diagram look like? When positive charges are accumulated near the surface, it means that the band diagrams near the interface should depict that the material is more of a p-type. That means if it was earlier only p-type, now it should represent that it is p+. P+ will be denoted by when the Fermi level moves much closer to the valence band energy and farther from the intrinsic Fermi level, obviously. Sorry. So let's draw now the changed band diagram, which is like this. I'll keep the top edge open of the oxide. Yeah, or like this. So now let us suppose that this was the equilibrium position, but now this is the new position of the metal Fermi level, EFM. So it has moved by an amount of this, that is QE, from the equilibrium position to the new position, Fermi level. And now what is going to happen alongside the p-type semiconductor? Now since I said that the charge carriers being accumulated in p-type means the positive charge is increasing, which means that the Fermi level should move much closer to the valence band energy. Valence band, but only along the interface, not along the depth of the semiconductor. Why? Because the effect of this electric field will be much more pronounced near the interface. That is why the interface is very important. It will be much more pronounced near the interface as compared to the rest of the body or the bulk. So along the rest of the body it will remain the same, and as is already shown in your book, you can see that the bands have bent upwards, whereas in the rest of the material the bands are again straight and are maintaining the same shape as in the equilibrium position. So let us see, since Fermi level for a function is see, it's fixed. Now the work function is also fixed, because work function is a function of doping only. We have EFP here, like this. We'll draw EFP. Okay, we'll draw EV here. We'll draw EI here. The same thing as it was for the equilibrium position. We draw EC here. More of a p-type means the Fermi level here is much closer to the valence band, so the valence band will bend upwards like this. It will move closer to the Fermi level. EI will bend upwards and EC will bend upwards, okay, along this portion. Now see, here the work function which was measured as the energy required for the electron to be moved from the Fermi level to the vacuum level should change because we are moving the Fermi level from equilibrium position to this position. But the work function, which is phi of m, is fixed for a material and is a function of doping only. So it cannot change. So it cannot change upon application of electric field E. So how do we accommodate this smaller work function? Is that because earlier we were measuring the work function from a Fermi level which was at a lower position, but since the Fermi level has raised to a higher position, that means the edge of the oxide conduction band has to bend. Alright, so the edge of this band is pulled upwards like this so that Q phi m remains the same, and similarly along this side it's Q phi s. Since the Fermi level is lowered, Q phi s remains Q phi p or Q phi s. Okay, let us just write it as Q phi p. Q phi p is lower, so bands are bending upwards. This is what is accumulation. Fermi level closer to the valence band means more number of holes. And okay, next one, which we take as the depletion. Depletion occurs when VGS is greater than 0. That means VGS starts getting positive. Take the equilibrium diagram, again this one, and we'll analyze that if we apply a positive potential to the metal gate, that is we deposit a positive charge, what will happen? An equivalent amount of the negative charge will be induced into the semiconductor. So the Fermi level will change its position. The Fermi level of the metal will change its position. The Fermi level of the metal will be lowered because now the electrostatic energy is increased and the electron energy is released. Remember that the Fermi level is related with the energy of an electron. So we draw, again I keep the top band open, and if earlier this was the equilibrium position, now the Fermi level of the metal has reached to a new position, that is EFM. It has lowered by an amount QV because this V in this case is positive. So the metal Fermi energy has lowered. Okay, and along this side, since an equivalent amount of negative charge has been induced, therefore the Fermi level of the p-type substrate will be raised, or it will move closer to the conduction band. So EFP, it does not bend. The Fermi level does not bend, but the band's edges, which is the valence band and the conduction band, they can bend. So if this is EFP, but now EFP has moved closer to EI, that is the intrinsic level. For the rest of the semiconductor, we'll first draw the same diagram as it was before. E V. Now along the interface, since we have to denote at the interface a material which is more of an n-type material, now which will be done by moving the Fermi level closer to the conduction band or closer to the intrinsic energy level. So the intrinsic energy level will bend downwards like this. So there will be a bending of the bands which is downwards. If we apply more of a negative charge, when more positive charge, if VGS is increased to a very large positive potential, what will happen in turn is that the EI will be further reduced. It will be bent down, and for some value which is VGS equals to VTH, this EI will move down along the interface. It will move down below EFP. Now when EI has moved down the Fermi level EF, when EI goes below EF, that is for any Fermi level of the material, when the intrinsic Fermi level goes below the Fermi level of that material, it becomes a n-type material. So that is what happens in the inversion. So now let us take up the inversion. So as I said, and yeah, one more thing. And okay, we have drawn the diagrams here. Now what about the work function? Q phi m here and Q phi p here. Now since along this side the metal, the semiconductor electrons are raised or increased, but here the electrostatic potential is increased, electron energy is reduced, and it has moved down, there will be a tilt in the oxide conduction band which will be like this. That means the edge will be pulled up along this side and it will be moved down along this side so that the value does not change, so that the value remains the same as in the equilibrium position. Okay, now inversion. Inversion occurs when VGS is equal to VTH. Now just quickly look at the picture of the band diagram. Again like this, oxide. Okay, alright, oxide. And then, if this was the equilibrium position of the Fermi level, we have, reduced it to this position, modified one, that is EFM, by applying VGS positive, but VGS equal to VTH. And along this side, what has happened is equivalent amount of the positive charge has been equivalent amount of the negative charge has been induced. Okay, so this one is our EF Fermi level, this one is our intrinsic Fermi level, this is the conduction band, and this is the valence band, EV. Okay, and then we have used a quantity that is Q phi. Q phi as the difference of the energy between intrinsic Fermi level position and the Fermi level of the material. So upon applying a negative voltage of a potential which is greater than this, what will happen? The bands will bend more because it will be more of an n-type. So under this condition, when VGS becomes greater than VTH, this EI goes below the EF. That means along this interface, the position of the EI is here. And just extend it like this. Now EV will go here, EC will go here. I use the same color for the band bending of EI, that is this. Alright, so it will be like this. Okay, now actual position is here, and if we take this thing as the bending of bands phi s, this is q phi f actually. Okay, so this forms a channel. At this condition, we say that the channel is induced in an N-type MOSFET. Now, let me first complete the diagram. Now, since the bands have bent down, the Fermi level has been raised. Therefore, the edge of the oxide along the substrate will be pulled high, and along the metal will be depressed, so that again the metal work function and the semiconductor work function value remains the same. Just extend it a bit. And here it is Q phi P or Q phi S. So it's from here to here, right? Now, let's look closer at this band diagram and note some important points. That is, at the interface, EI is below EF, but in the body, EI is greater than EF. As you can see, EI is above EF means EI is greater than EF. Here we can see EI goes below EF because of the band bending. Now EI is greater than EF in a p-type semiconductor, as is the case because this we know is a p-type material, and at the interface EI is less than EF, which means it's an n-type material. So how do we get this n-type material from a p-type material? Are these two different materials? No, this is simply a p-type material, but in which we have induced an n-type channel by way of the application of the external voltage. We have externally applied the voltage and we have induced the charge carriers, or we have attracted the minority carriers which are present in this p-type substrate towards the interface, and this part forms the channel of the MOSFET. And this condition occurs when VGS is equivalent to VTH. That means channel is induced. I again repeat, channel is induced in the MOSFET when VGS is equivalent to VTH. Now, how do we define this VTH? VTH, which is the threshold voltage, a very important voltage in the operation of the MOSFET. VTH is defined as a voltage when strong inversion is achieved. Now, how do we say that when strong inversion is achieved? So, we can quantify this. Strong inversion is achieved when phi s, that is the band bending, is equivalent to twice phi f. See, phi s is the surface potential which tells us about the bending of the bands at the surface or at the interface. This is x equals to 0 at the interface. Alright, so if phi f is an amount by which EI is above EF in a p-type substrate, then the channel should be strongly n-type as the substrate is p-type, which means at the interface this EI should go below EF by the same amount by which it is above EF in the rest of the semiconductor. So it is twice KT by Q ln of Na by Ni. So it means that the channel should be as strongly N-type as the substrate is P-type. And how do we quantify this N-type and P-type? It's simply from the relative bending of bands. I hope you can now understand this energy band diagram. If you have any queries, you can write to me at Anasha and subscribe to my YouTube channel. Anna Farkanda.